where we are having sine squared cos 3x. So we have to integrate in terms of, right? So the first thing we do, we inspect, we're having let's say trigonometric function which is to the power of 2 and cos to the power of 1. But the coefficients of angles differ. Number 2, the coefficient of angles differs, and number 2, we have one which is square. So you are having a product of two functions. Product of two functions. Now, even if let's say you wanted to close and say what is the derivative of sine, we have to get cos x, isn't it? Not cos 3x. So which means this is not the function which gives us that derivative. Number 2, even if let's say you thought of cos 3x when you derivate already, it can't give us a square. Sine square. You will think of what we call those coefficients of sine and cosine which have different cosine, what is it? Different coefficients of the angles, where it's a half identity leg. So if you think of that, but it's this is a square, so you cannot apply that one because the other one is a sine squared. You don't have one where you have a sine squared. So which means you have to try and think, what can I do at least if I try and drop down the exponents? Dropping down the exponents. So I wanted to look into that formula of halves. Halves, where is it? Try and think of this product of sine and cosine with different coefficients. With different coefficients. So I hope you see there's none where you have a sine squared or cos squared, which means at least it must be sine to the power of 1. So even if you are tempted to try and utilize this in the initial step, so it will be math error because we don't have one which is square. But we know that we can move on to other identities. But can we not drop down the exponent of x by using identities? So we know that there's this identity, the cos 2x, isn't it? But making sine squared subject of the formula, we know that sine squared is equals to, I think it's 1 over 2 minus 1 over 2 cos 2x. So thinking of that identity then. So we know that sine squared is equals to half minus half cos 2x. But according to the general formula, is cos 2 equals to 1 minus 2 sine squared. The general one. So that's the one at least it will help us to drop down the exponent. So utilize that identity. So let us utilize that identity, therefore, in the integral of that function. So we know that sine squared can be half minus 1 over 2 cos 2x in bracket. I hope you see I have substituted sine squared, which is equals to half minus half cos 2x. Therefore, it is still multiplied by cos 3x dx. Then in that case, we can multiply out that bracket so that we can integrate and see the functions that we're having. So therefore, half times cos 3x. So I have, let me factor it out there. So we have half times cos 3x multiplied by dx. Then the other one, it will be cos times that. It will be our minus integral of, we put a half. These two are multiplying each other. Cos 2x cos 3x dx. So I'm just expressing them as sum or difference of functions accordingly. But if you want, you can have it in one bracket, having half cos 3x minus half cos 2 times cos 3. I hope that is clear. So that's multiplication. So focusing in our function. So we know that derivative of sine gives us what? sine function. Or what did we derivate to get the cosine function? At least this is to the power of 1 and an angle. So we know that we derivated sine of the same angle to get cos 3x. So, but what was missing, it is the constant. Yeah, there's the constant derivative of 3x, which was 3. So we have to divide by the derivative of the angle there, which is 3. Because it was missing there in the function that we have on top. Now, moving to this second one. So we try and do inspection that we have product of two functions. But if you say you want to look into this, say this is the function, this is the derivative, it won't be true because the derivative of cos, we cannot get cos 3x. So here we have now, though it's a cosine and cosine of different coefficients. So we have to think of that identity. We have to think of these identities now. The product of cosine and sine. So we come in. So if it's cosine, cosine, we know that we're going to have half cosine A plus B plus cosine A minus B. So if it's cos and cos. So we still have our negative half. So please, I hope you see that half, I didn't lose it. But according to the identity, if we have to replace this, it is a 1 over 2 into. So it states that it is cos, then 2x plus 3x, which is 5x. Therefore, plus cos, it is 2x minus 3x. So it will be minus x, isn't it? Okay, close shop, dx. So the brackets are very important. I hope you see what is happening. So we're substituting half cos 5x plus cos negative x dx using the identity. So when integrated, please don't lose the integral sign. We're still substituting. So simplifying this first term, we're going to have sine 3x over 6. Then the second one, in the meantime, we can integrate. I hope you see. At least we have product, not product, sum of functions. We don't have what we call multiplication. It's just sine, cosine on its own, cosine on its own. So we can integrate. But in the meantime, let's multiply this and have negative 1 over 4. So integral of cos 5x is going to be integral of cos 5x. Integral of cos 5x. It is sine 5x all divided by 5 by the derivative of the angle. So same thing, we're going to have, we divide here. Okay, this is still plus. So it's going to be sine, therefore negative x all divided by the derivative of the angle, which is, we can say negative 1. But according to trigonometry, it was fine that we know that in the fourth quadrant it is positive, so we're supposed to leave it as positive. As positive, I hope you see. So, but we're just working with the negative, is still fine. That even if, let's say you are here, if you wanted to say, oh, sine at the fourth quadrant is negative, we're going to say negative, you'll still get the positive. I hope it's clear. But to work with this one, you're not forced to reduce the angles, do reductions of angles. So let's leave the final answer in just simplification over 6. Okay. So this is going to be negative 1 over 20, right? 5x all divided by 25 times 4 is 20. So then the negative multiplies this negative. We're going to have what? Positive. So plus 1 over 4 then sine negative x there, space. Okay, I want to close it, close it. Then plus the constant, plus the constant. So that's the answer we're supposed to have. That's the answer we're supposed to have. Okay, I hope that is clear, well understood. So always when you're in trigonometry, in fact in integration, let's just put it in this standard way. What did you derivate to get these functions? So if you see you're trying to check if I derivated maybe sine to get cos 3x and integrate and having that in your own way, please make sure it must resemble the formula. Do not utilize your I don't know your brain and say that no, I know the derivative of sine is cos. We know it's cos, but look into the angles or the coefficients of angles, but to the powers. No, it's not. No, it's not wrong. That's why even here I did it in that way. Say 1 over 4. 4 is still dividing sign. Doesn't matter. 1 is still multiplying sign. And here we still have 1 over 20. 1 is still multiplying sign. And it's divided by 20. This around 4. Around 4 marks. Yeah, 4. I avoid the rearranging. Just use the formula. But it will still give you the same answer. It will still give you the same answer because here it will still be 5. Here it will be still x when you subtract. Because even here the final answer must have negative 1 over 4. If you rearrange, this negative will multiply that positive, you're still gonna get it will still multiply that negative in there. It will still have negative. Because here we have the negative here. If you do call it the reductions. It's not the reductions of angle, it's making the angle of sine and cosine positive. So you'll have negative 1 over 4 sine x. Okay, I hope we can. Oh no, time flies. Time flies. Okay, people are still coping. Go to division by applying integration by applying how do you write division. So I want us to look into division by applying long division. So I want us to look into division by applying integration by applying long division. So I just want to take an example where, so I apply it when the exp is greater than the numerator. So apply long division, let's say for an example, when the exponent is greater than the numerator, or or the exp is when the degree, let me say degree, or degree of exponent is equal between the numerator and denominator. Between the numerator and denominator. So we'll apply long division in a case when the degree of exponent is greater than the numerator, or there is equal, or the degree of xp is equal between the numerator and denominator. So we'll apply long division in that case. So I'll take at least 2 examples to explain that. Just want to take 2. Okay, I'll start with the basic one. So let's say for an example, we have integral of, let me say, x squared plus 1, all divided by x. Therefore, we'll have dx. Okay. Let's say for an example, if it was not explained that utilize long division to integrate. Remember, always you start by inspecting. We inspect both numerator and denominator if here we have a quotient of functions. And we normally check the denominator. If we derivate the denominator, are we going to get the numerator? That's where we think of ln of the denominator. But when we inspect this one in the denominator, I hope we see the degree of exponent is even lesser or lower than the one in the numerator. So you cannot think of the ln of the denominator, because we know the derivative of the denominator, it won't give us the numerator. So which means we have to think of other rules. So in this case, in applying long division, okay, what else that I wanted us to think of? Yeah, that's the case. But make sure, make the formula sheet your friend, because when you simplify your problem, it must resemble something in the formula sheet. It's either it's a power rule, natural logarithm, or inverse trigonometric functions. So it's either the power rule, trigonometric functions, inverse trigonometric functions to say, or the last one, it's either we have the natural logarithm. When we integrate the natural logarithm, ln of x minus a over x plus a. It's there in your formula sheet. So please, when you're in this part, think of that. Between partial and long division, it must resemble that in your formula sheet. But let's not waste time. So this one, you can solve it in 2 ways. It's either you can apply what we call, when we simplify, using the rule of, what we call that rule, loss of fractions, splitting the numerator between, sharing the denominator to say, so you can do that. So you can say x squared divided by x and 1 divided by x. It gives you the answer. But I want to pass by long division. Always we are going to take, we call this the dividend. We put it inside the root. The one which is being divided, you put it inside the division. And the divisor, you put it outside the root. So then when you start, you want to integrate. We will not integrate. We are saying we are dissolving this into a long division. We are always going to say that x squared divided by the divisor, the x. So what we do, the first term of the, what can I call that? The dividend, you always divide it by the first term of the divisor. And when you're done, you write your answer on top of the division. You write your answer there on top of the division. Okay. Just want to use a different color here. Let's do this. So you always do that after the answer that you get after dividing, you write it on top of the division. So we know that x squared divided by x is what? We're going to get x. We're going to get x. In fact, maybe I was supposed to write the sequence. We always divide. From division, we multiply. From multiplying, we subtract. That is the sequence of long division. So we divide, multiply, and subtract. Divide, multiply, and subtract. So please, you're not required to write this. It's just for explanation. Just for explanation. So you just have to divide x squared divided by x. It's going to be x. When you're done the sequences, you must multiply. So we're going to remultiply again by the divisor here. So it's going to say x times x, which gives us x squared. From there, we're going to say we want to just draw a remainder line. Draw a remainder line. After drawing a remainder line, we're going to say we want to subtract that expression. So subtract that expression from the top one. So we're going to say x squared minus x squared is, let's say 0, isn't it? So we have 0. Therefore, we'll say 1 minus 0, you still have 1. Or normally we say you drop it down if it doesn't have a like term. You just drop it down. But it was subtracted by 0. Then from there we could divide further, but we always stop dividing if we have a constant or if we have a 0. I hope that is clear. In long division, we stop dividing if we have a constant or when we have a remainder of 0. Then we can conclude that our answer, though we're in integration, we're going to say our answer after dividing this. Our answer that we got, it is x. And what is the remainder? That's 1. We can still divide it further by x. That's how we write it. Therefore, still have dx there. So we conclude our answer is x, the one on top of the division, and then with a remainder of 1. We could still divide further by x, but we'll be now adding x in the denominator, so we'll have a rational function there. So we just stop there, that we can still divide further. So after that, we can integrate after we have dissolved into long division. So we know that integral of x is, it's x squared, isn't it? All divided by the exponent. Therefore, plus integral of 1 over x. Yes. So we derivated ln x to get 1 over x. Therefore, plus a constant. What do we call this? It works with the product of functions. Number one. With quotient of functions, I always say go straight away and think of ln of the base. But if the base is not giving you the derivative of the numerator, we have to think of simplifying. Then, but if you can't simplify, if you had one function in the denominator, please think of inverse trigonometric functions, most especially when there's a square root. So when there's a square root in the denominator, think of inverse. But even if you see the numerator, there's inverse trigonometric function. The most especially the arc sine, when we integrate, I think it's x over a plus arc sine x over b, or x over a to say. In your formula sheet there. I think it's a squared over x plus arc sine x over a. But make the formula sheet your friend. Please don't force thing. If it doesn't work and if you try and derivate, it doesn't take you back, then there's a math error. It's math error. But in algebra, please don't mix inverse trigonometric functions where you can use U substitution and where you have to use partial fractions. So you need to use R equal of the algebraic functions, only in algebraic functions, where we have x squareds and 3x cubed. Okay. A simpler example number 2. If we have integral x cubed minus 2x squared plus x minus 2, all divided by x squared. Listen, I took the simplest one. This is the simplest. So I'm looking when we divide, it will look easier. Okay, but nonetheless, it's just for explanation. We inspect well algebraic functions. First thing, okay, can we take it to long division? Therefore, taking to long division, we check, oh, the exponent is greater. in the numerator. So which means we can apply log division. Therefore, we take the dividend, we put it inside the root, we'll have minus 2x squared plus x minus 2. Then the divisor, we put it outside the root, which is x squared plus 1. So according to the rule, we always divide the first term of the dividend by the first term of the divisor. But just for explanation purposes, I can just write it x cubed divided by x squared. So what is x cubed divided by x squared? So the answer that you get, you write it on top of the root. So we get x. The rule says that you must remultiply after dividing. So it's divide, multiply, subtract. So we're going to say x times x cubed, x squared to say it's x cubed. Then x times 1, or rather x times 1. So we have positive x. So after remultiplying the dividend by the answer we got on the top of the division, now we say we want to subtract. You're the one who introduces the bracket and the negative sign. This whole expression, we need to subtract it. So x cubed minus x cubed is? So x cubed minus x cubed. So I have 0. Therefore, minus 2x squared minus x. So it's minus 3. Minus 3? No. So I have minus 2x squared. It doesn't have a like term, so you drop it down as it is, always subtract by 0. So we have minus 2x squared, is there? And then x minus x. So it's 0. It's 2 minus x squared. Remember, we have negative 2x squared. Do we have negative x squared term here? No. So it's 0. It's subtracted by 0. It still remains the same. So therefore, you say x minus x is 0, isn't it? Yeah, x minus x. So it's 0. So please, in N5, I just forgot to explain. We can't write terms in this way. That we say subtract this. That's what we're doing always. So then you know that this is going to be eliminated. Negative 2x squared is the answer. X will be subtracted by x, and you'll be left with what? With minus 2. So when we say subtract the bottom part from the top one, that's what we mean. So you write it in this way if you're still practicing at home. So negative 2x squared minus 0 is still minus 2x squared. Then x, it has a like term that it can subtract, which is x, goes to 0. Then minus 2 minus 0 is still minus 2, isn't it? So we need to continue further and divide until we have a constant or 0. We start again. The first term of the answer that we got, it must be divided by the first term of the dividend. So negative 2x squared divided by x squared. The answer that we get, we must write it on top there. So I'm avoiding a lot of lines. So what is negative 2x squared divided by x squared? It's negative 2. The rule says that we must multiply after getting the answer. So it's negative 2 times x squared. So I have negative 2 x squared. Then negative 2 times 1. So I have negative 2. So please pay attention to this. The remainder, you must say we want to subtract this expression now from the top one. We subtract. So we're putting a negative sign by ourselves. I think let me put it in black to show that we are subtracting. So we're going to say negative 2x squared. Okay, plus 2x squared. Negative 2x squared plus 2x squared, so it's 0. Then minus 2, does it have a like term here? Plus 2, so we get 0. So we can conclude our answer that if we have divided, therefore our integral, if we have divided the top one, is going to be equals to, our answer is x minus 2 dx. The remainder is 0, so you cannot say 0 divided by 2. So we have divided, the remainder was 0. So we can conclude that this is our answer when we divided the top expression. Now the integral now would be equals to, it is now power rule here. So we're going to say x squared divided by 2 minus integral of 2. So it's going to be negative 2x plus the constant c. That's how we utilize long division. So it takes you back to N4 where you were utilizing cubic graphs, or to N3 where you were dealing with what was this, cubic graphs again. Or if you once did N1, it takes you to N1 where you're dividing cubic functions and by, let's say, linear functions. Okay, I hope we can conclude it there.